Welcome back, Calculus. We are in section 1.3a today, continuity. I've got the checklist on the screen, so I'm going to force a pause on your screen. You know what to do from here. All right, so before we look at the formal definition of continuity, let's go ahead and talk about it informally. You don't need to write anything on this screen. Let's just sort of discuss continuity. So informally, a function is continuous at a point x equals c if it's unbroken there, so there are no holes, jumps, or gaps. Another way we talk about it is that we can draw that function without picking up our pencil, okay? A function that's continuous on the entire real line is said to be everywhere continuous, okay? A function that's not continuous at x equals c is said to be discontinuous there. So I've got two graphs on the screen. Which one, the one on the left or the one on the right, is continuous? The one on the left is continuous everywhere. The one on the right has what we call an infinite discontinuity, and we'll talk more about that here in a bit. So there are three conditions that are needed in order for f to be continuous at a point x equals c. I'm going to force a pause on your screen. I'd like for you to copy my screen and we'll fill it out together. All right, so if you look at the graph on the right, it's basically that kind of has it's a line with a hole in it. Would you say that that function is continuous at x equals 2? No, it's not. What is missing? What do we not have at x equals 2? We don't have the function value, right? So that is something we need to exist. We need the function value. I'm going to call it f of c. In our particular example, it's f of 2. So f of c needs to exist. Okay, now looking at our example, does the limit exist for this example as x approaches 2? As x approaches 2, the limit does exist, okay, and that's another condition we need. But we can see that that's still not sufficient, right? Because the limit exists in our example, but our example is not continuous, okay? So let's say I add a function value here at 2. So let's say, okay, now I have f of 2. So I've got that the function value exists. I've got that the limit exists. However, is the function continuous? It is not. What do I need to do with this purple dot in order to make that graph continuous? I need to move it up, right? In other words, I need that function value, this piece, to equal the limit, right? And that's my third and final condition. So let's write that. I need for the limit as x approaches c of f of x to be equal to the function value at x equals c. Okay, so if you've got all three of those conditions, then you have proved that the function is continuous at x equals c. If any of those fails, the function is not continuous at x equals c. So to convince ourselves that we need all three of these conditions, let's go ahead and try to draw examples of graphs where one of the three conditions fails and see, okay, yeah, it's not continuous if one of these fails. So I'm going to force a pause on your screen. Will you go ahead and copy what I have? All right, so let's try to draw a graph where the function value, f of c, does not exist. Let's go ahead and have the limit exist still. So one example of that, kind of like what we had in the beginning, right, with that red graph. Make sure this passes the vertical line test. Okay. I am going to force a pause on your screen. Now you try the other two, okay? So try to draw a graph where the limit does not exist, but the function value does. And then on the last one, we want both to exist, but we don't want them to be equal to each other. Okay, so try those. When you're ready to see potential answers, go ahead and hit continue. All right, so I've got potential answers on the screen. Of course, answers will vary. But here we've got a graph where the function value exists, but the limit does not. Is the graph in the middle continuous? No, it's not, right? I'd have to pick up my pencil in order to draw that. And then that last one, they both exist, both the limit and the function value exists at x equals c. However, they're not equal to each other. So is that last graph continuous at x equals c? No, it's not. Again, I need to pick up my pencil in order to draw it. So you can see all three of these conditions are necessary in order for a function to be continuous. So we've got two types of discontinuities. So on your paper, I'd like for you to write removable discontinuity and non-removable discontinuity. And we can classify them in these two main branches, okay? The removable discontinuity for mathematicians is the least aggressive kind of discontinuity. So for a removable discontinuity at x equals c, the limit as x approaches c still exists. Okay, so algebraically speaking, this is where you're going to have a hole, right? So you may have something like that. Again, the function value may exist or it may not, but the point is the limit does exist. However, it's discontinuous because either the function value does not exist or the function value is not equal to the limit. Okay, now for non-removable discontinuity, you guessed it, the limit as x approaches c of f of x does not exist, okay? And there are kind of two subcategories here that we look at in calculus. You've got a jump discontinuity, okay? And in this case, you have that the limit as x approaches c from the left and from the right exist, but they don't equal each other. Okay, so the left and the right hand limits both exist, but they're not equal. Okay, can you think of a parent function that we've studied that is has a jump discontinuity? Yeah, how about the signum function? Broken railroad tracks, right? Okay, so signum would be an example of a jump discontinuity. The other kind is an infinite discontinuity, and this is where the limit as x approaches c of f of x goes to infinity or negative infinity. Okay, so this is going to be like a vertical asymptote. Okay, so go ahead and pause your screen if you didn't get all that, and then come back in when you are ready. All right, let's try a couple examples. So this is example 1. Go ahead and write this on your notes, or in your notes. F of x is x minus 6 all over the quantity x plus 4 times the quantity x minus 6. And the directions say to find the x values, if any, at which f is not continuous. And then we want to label basically the discontinuities as removable or non. Remember, for a removable discontinuity, does the limit exist? Yes, it does. Okay, so we first want to look at our discontinuities. Now remember, if the function value does not exist, that's automatically a discontinuity. Okay, so how do I find basically pieces of the domain that the function value does not exist here? If you remember from Algebra 2, you look at the denominator, right? If you were to find the domain of this function, values you would need to exclude, we'd look at the denominator because 0 on bottom is a no. The function value would not exist there. Okay, so my discontinuities, let's write that, are at x equals negative 4 and x equals positive 6, right? Whatever x values would make the denominator 0. Okay, so now we're going to go find the limit at each of these two. Let's start with the limit as x approaches negative 4 of f of x. Okay, well, if I plug in negative 4 in the numerator, I get negative 10. What happens in the denominator? We get 0, right? Is that a do more? Nope, that is a DNE, okay? So the limit does not exist here. So does this mean that at x equals negative 4, we have a removable or non-removable discontinuity? We have a non-removable discontinuity. All right, let's go ahead and do the same thing for the limit as x approaches 6. Now if I plug in 6 to f of x for x, what happens? I get 0 over 0, right? Make sure you show that. And that means do more? Absolutely. So notice this is already factored for us, which is great. So the x minus 6's go away. So now I have limit as x approaches 6. Don't forget your understood 1 in the numerator. all over x plus 4. This limit does exist, right? I get 1/10. Since the limit exists, this discontinuity is removable. Great. All right, for example 2, I'm going to have you do this one on your own. So go ahead and write g of x on your screen. G of x from my screen on your paper. And notice that g of x does factor into x plus 1, x minus 1. There's only one discontinuity in this case because there's only one x value that makes the denominator 0. Okay, make sure you're only looking at the denominator. And then go ahead and classify that discontinuity as removable or non. Hit continue and you're ready to see the answer. So the only discontinuity here was at x equals 1. It's a removable discontinuity because the limit does exist. Okay, the limit is 2 when you try to find that. Now I did want to give you a caution here because if you graph this on a graphing calculator, which has, good old 96 pixels, you're not going to be able to see that discontinuity, okay? Because notice when these factors of x minus 1 cancel, you're left with the function x plus 1, which is just a line with y-intercept of 1, slope of 1, and you don't see that discontinuity with such few pixels, but it is there, okay? So I do have a hole at 1, 2. Again, you just won't be able to see it on a graphing calculator. All right, another thing I wanted to point out was this discontinuity was removable in a sense because I'm able to remove the factor associated with x equals 1, correct? So let's go ahead and put that in words together. So if the factor x minus c cancels, in other words, you can remove it, then x equals c is a what kind of discontinuity? Is a removable discontinuity of a rational function. Rational fractional, right? All right. Okay, let's look at a couple other types of functions. I'm going to force a pause on your screen and go ahead and write example 3 and example 4 in your notes. All right, so example 3 is what kind of function? Example 3 is a piecewise function, okay? So I like to really analyze each piece. In this case, I've got 2. I'm going to call it the top piece and the bottom piece. So the top piece is valid for all x's less than or equal to 0. So for those x's, does that give me the left-hand limit, the full limit, the function value, or the right-hand limit? So this gives me the left-hand limit as well as the function value, because of that equal sign, right? So all x's less than 0 would give me the left-hand limit. X equal to 0 gives me the function value, correct? And then the bottom piece is valid for all x's greater than 0. So what would this give me? This gives me only the right-hand limit, okay? Now, for a function to be continuous, I need the left-hand limit to equal the right-hand limit, so that the limit exists, and then I need the limit, the full limit, to equal the function value, all right? So let's find these limits. Let's take the limit as x approaches 0 from the left of h of x. So would I use the top piece, the bottom piece, or both for this? I would use the top piece. So this is going to be, if I plug in 0 for that expression, I would get 0 plus 1, which is 0. Okay, now let's find the limit as x approaches 0 from the right. In which case I would want to use the bottom piece, okay? So if I plug in 0 for x into the bottom expression, I get 0 squared plus 2, which is 2. Sorry, that should be 1. So does the limit exist? The limit as x approaches 0 does not exist. since the left and the right hand limits are different, okay? Now, would this be a removable or non-removable discontinuity? This would be a non-removable discontinuity since the limit does not exist. And would you classify this as a jump or an infinite discontinuity? This would be a jump because the left and the right hand limits both exist, but they're different from each other. And this is a non-removable. Okay, how about example 4? What kind of function is that? What's the parent function there? Parent function here is the signum function, so let's go ahead and write that. Always you want kind of a light bulb to go off when you see those absolute value of something over itself. So this is the signum function shifted which way? Shifted to the right 2. Now keep in mind that the y values are still +1 and -1. You've just shifted it to the right, not up or down, okay? So now that I have the graph, I can easily determine, do we have a removable or non-removable discontinuity here? It's a non-removable because because the limit does not exist, right? So non-removable discontinuity at x equals 2, right? Specifically, this is a jump discontinuity. All right, I'm going to force another pause on your screen. Can you write examples 5 and 6, please? All right, so for example 5, if I've got a rational function to determine the discontinuities, what did we do first? We looked at the denominator and tried to factor it, right? Now, this is not factorable over the reals. If I try to set that equal to 0, what's going to happen is I get an imaginary number, right? So no real solution. So there is no real values that would make the denominator 0. So in this case, no discontinuities. In other words, everywhere continuous, okay? What about sine? Can you draw that in the arrow for me? Remember, sine is just a wave, right? Any discontinuities? Not for sine or cosine. The 3 just is a horizontal compression. So again, no discontinuities for sine or cosine. Those are nice continuous waves. All right, here's our last example. I'm going to ask that you bring this one to class. So I want you to try to write a function, and it can stay in factored form. And I want it to have a removable discontinuity at x equals 5. Okay, so bring this one to class, and we will discuss from there. Thank you all, and we will talk next time.